Okay, so our fifth and last part of week six lecture is going to be about design for the additive manufacturing. So the design for the additive manufacturing, sorry, it doesn't work here. Design for the additive manufacturing, or the DFAM, is a design for manufacturability using the additive manufacturing or 3D printing technologies. The DFAM is going to increase the efficiencies and the design flexibility and synthesizes the shapes, the sizes, the geometric mesostructures, and the material compositions and the microstructures to best utilize the additive manufacturing process capabilities to achieve the desired performance and the other life cycle objectives. So the DFAM can cover the shape, the materials, and the hierarchy complexities very well. So it's about different from the traditional manufacturing. This additive design process empowers the engineers to create more intricate shapes and production parts while reducing the weight and the material consumption. So it is a complete reversal of the conventional ways of thinking about the design. So, for example, the DFAM is a collection of the rules and the best practices that designers and the engineers must follow to achieve high level of success in 3D printed parts designs. When manufacturing complex parts, 3D printing is often going to be the best choice than any other standard manufacturing process because it first requires no molds or other expensive tooling. Also is going to be offer some considerable geometric flexibility and the customization and has only a limited materials waste as only of the material required for the make the part. The design goals for the DFA is first, create a lighter, stronger, and more efficient designs. Second, reduce the part costs. Third, enhance the sustainability and increase the performance. In all the cases, is going to improve the innovation. So, design for the um, AM is going to show you an example of its importance here. So this drawing of the part rendered above the reveals of the difficulty of the designing tall walls and other special features using 3D printing. So you can see here we're going to have multiple walls, multiple holes, different shapes. Some of them actually can be enclosed within the part and still can be done without any assembly process. Um, So the small gas features also going to pose a difficulty for 3D printing. The plastic affected by the gravity and wants to sag or warp, and given the chance, um, if given the chance. The approach of the DFIM is first generative design and to create and iterate a designs that meet the given set of the input criteria for the application. Also, is about the part constellations, where to constellate multiple parts into a single one. The topology optimization, which about the optimize the best distribution of the materials to maintain a crucial specifications for the parts, such as the weight, the stiffness, and the strength. So the DFAM incorporates the consideration involving the choosing technology to print your parts, the part geometry, the material used, and any post-processing steps needed to strengthen the or improve the look of your part. The design guidelines for the DFAM are first about the wall thickness. So you don't have to make it too thick or not too thin wall. The self-supporting angles, low over gravity, heavy areas tend to sag or warp as the parts are going to be built, so you want to ensure that any features can support its own weight during the build by the using of the smooth transitions to control the potential sag. Different from the self-supporting angles that offer the smooth slope to a part design, the overhangs are abrupt changes in the part geometry. For the metal 3D printing, any overhang greater than 0.02 inches or 0.5 millimeters should have an additional support to prevent the damage of the part during the build. So the minimum feature size for each printing processes, you can have different capabilities to print the small features. Like for example, for the SLA, it's going to be something like 0.0632 millimeters as the minimum feature size. The DMLS is going to be 0.153. The FDM digital printer is going to be zero point 0.2. The FDM Industrial is going to be zero point 0.2. For the PolyJet, it's going to be 0.3 or 5 millimeters. For the Carbon DLS, it's going to be 0.5 or 8. For the MGF, it's going to be 0.05 millimeters. And for the SLS, it's going to be 0.7 to 6 millimeters. The internal channels are going to be very possible to be done by using the additive manufacturing. Well, you can say, okay, now we can do something similar to that by using the casting, if we're going to use the lost wax or similar processes, but it's going to be about how we are going to make the core for this part is going to be one of the hardest tasks you can have. Anyway, for the internal channels, when designing internal channels, consider the rules of normally associated with the design for the 3D printing, especially the strategies behind the printing overhangs and the minimum feature size. The FDM is good choice for the printing channels compared to the SLA. There are some post-processing techniques that can be helped to improve the texture if rough internal channels are not avoidable. Internal channels do cost more and take longer to print due to the complexity of each part. The part orientation also is going to be one of the important things. It's about how you're going to do the slicing and which way you're going to print. So some directions are going to be more efficient than the others and may improve the strength and build quality. So determining what should be the z-axis, the one which is the part going to be grows up from, turns out to be a crucial. A simple rule can be applied. If the part must be endured to a compressive force, we will print it we're going to print it with the layers running parallel to the direction of that force. The surface finish also going to be affected by the part orientation during the printing. So for the smooth part, we print so that the layers are going to be parallel to the part surface. And if the process is going to be involved the builder plate, then it can act as support that will going to provide the smooth surface finish to your parts. So these are some of the principles for 3D printing design. We can see that actually, depending on how you again, what will be the part you're going to make, the supported walls or the unsupported walls. Sorry for that. Support and overhangs, the imposed engraved tills, the horizontal bridges, the holes, the connected moving parts, the escape holes, and the minimum features, and the pin diameters and the tolerances. So with different processes, what will be the dimensions that we can achieve from that. So example of the DFAM is the failures in the 3D printed metal parts without the DFAM, and this is for the water spray block. So you can see actually there are some of the defects has been occurred due to the process, like for example the surface roughness and the internal design have been done. So you can see here the implementation of the FAM in 3D printed parts via the coupled finite element methods and the computer fluid dynamics and the analysis to redesign the process until we're going to achieve the best design. And that will be the successful 3D printed metal part redesign with the FAM. So you can see that the weight has been reduced by reducing the density of the parts itself. The channels, of course, has been optimized to have the best flow with less pressure loss. Okay, so by now we just finished the all the section of today lecture, and for next week we're going to talk about the motion analysis and rigid body dynamics, and reading is going to be the lecture, tutorials, and the practice notes. So thank you for your attention, and hope to see you very